Hi everybody, and welcome to the third and last Intel IoT webinar. I am Beatrice from BMI App. We organized this series of webinar with Intel. So I am here with Yorick and Dirk from Intel and the Diabetes Helper team, who will present to you in a few minutes their device. So for those who have not attended the webinar before, how does it work? Well, you can ask all of your questions via chat, and we will answer them immediately. Before giving the hand to Yorick, who will present the Intel Edison and IoT in general, I would like to ask you a question by poll to know you better, and so we can make more personalized webinars, even more personalized webinars next time. So let me launch the poll now. We just give you 10 seconds more to answer the question. So I will close the poll now. And give the hand to you, Yorick.
Thank you, Beatrice. And I'm assuming you can all see my screen by now. If you can't, Beatrice, just shout if I need to do something different. Hey, hi everyone, and welcome. As Beatrice said, this is our first IoT Innovation webinar. So my name is Yorick Shedgin. I work at Intel, and I'm in charge of our IoT inventor and maker platforms for the EMEA market. In the webinar today, some of you may have attended previous webinars, so you start to know some of the structure. The idea is really to give the floor to some of the inventors out there. But before that, I'll give this quick introduction on IoT innovation, generally speaking, and what Intel does in this area. And then we'll have a team based in Israel that has developed a diabetes helper solution. And they've actually won our Make It Pro challenge earlier this year. So they'll take most of this webinar actually to go through the solution that they have developed, and then we'll wrap up at the end of this. So IoT innovation. So before we talk about IoT, the innovation part, obviously there's the Internet of Things opportunity, which is massive, and we have a couple of numbers out there from analysts. This one comes from IDC, but it identifies about 50 billion connected devices by 2020, which is a huge potential. And these devices span from home automation device to healthcare, the industrial sector, things around the smart cities or transportation, So there's really multiple sector of the industry and of our lives that are touched by this IoT. Now, to me, the more interesting part to look into is where the innovation is coming from when you look at the Internet of Things. And a lot of the innovation is actually coming from entrepreneurs and startups, inventors, who get really creative about solving some of these issues that we have in our daily lives or in some of these industry verticals. And come up really, really fast with some prototyping and be able to go to market and productize their solution very, very quickly. So a lot of the innovation is coming from there. And I think there's a couple of elements that underpin this trend, but I think the one word that summarizes the reasons for this trend is the word accessibility. And you have accessibility at all levels, think of it from a sales perspective with online sales and much easier access to online store and sometimes even physical stores linked to online stores. From a crowdfunding perspective, if you look at the financing part, the software tools are getting easier to use. But then the last bit to this, which probably came a little later, is the access to very easy to use hardware prototype and development boards. And this actually complements the other areas and provides a very good mix for startups and innovators to go and really get from idea to prototype to production and go to market. So the other thing I wanted to cover briefly in this introduction is what is Intel doing about this and how we are supporting this trend and the industry around the Internet of Things. And I wanted to touch on two elements specifically. One is from a product perspective, and then on the next slide I'll talk a little bit about some of the programs and support that we have for this ecosystem. So from a product perspective, there's been a couple of products in the past, but I think the latest product that really fits into this space is the Intel Edison development platform. And this platform is really developed to lower the barrier to entry for developing hardware devices. It's a sort of full computer in something that is just about the size of an SD card. So that gives you a sense of how small this is, but it packs a lot of technology in there. It has dual core Atom. It has a microcontroller in addition to that to go and listen to all the sensors that can be connected through 40 GPIOs. It has 1 gig of RAM, 4 gigs of storage on the board itself, and then it has all the connectivity you need with Wi-Fi and Bluetooth Low Energy. And all of this is packed in a very small form factor, which essentially means that you can use this with some expansion board for early prototyping, but you can then move from the first sort of ideation quick prototype to a more evolved prototype, and eventually to a production-ready platform that allows you to go to market. So from a product perspective, this allows you to go from ideation to production with a single platform. So that's one of the area I wanted to touch on more on the product size. The other piece I wanted to cover on what Intel is doing around IoT is in terms of these supporting programs. And there's two things I mentioned here. One is the Internet of Things Ignition Labs. We have a couple of these labs, 5 and expanding to 7 and 9 in the next few months in various cities. So we have one in the UK, we have one in Germany, one in Israel, one in Sweden, to name a few. Russia is also coming on board with Moscow. And these are spaces where you get access to engineers and some equipment It's available for large enterprise, but also for startups if you want to come over and optimize some of your projects. So that's one element. The other one is called Challenge Up. And Challenge Up is it's essentially an IoT accelerator program. And this is a joint initiative by Intel along with Cisco and Deutsche Telekom. And we're still in the recruiting phase. So if you Google Challenge Up, you'll get to the page where you can sign up, submit your ideas, and these will be evaluated. And if there is the best ideas will actually be selected to get into this IoT accelerator program for the next couple of months. So there's many other things we do besides these, but I think these were two very important initiatives that show a little bit how Intel is supporting the ecosystem. So with that, I will close on this introduction, and I will leave it up to the team in Israel to go and talk about their diabetes helper solution. And I'll give the floor to Omri, who will talk about their solution.
Hi. Can you see my? I hope you can see my screen. Just a second. Okay. So my name is Amin. I will talk to you this lecture about trying to make an idea a product. Too often papers with algorithmic solutions to medical problems remain just a paper in an engineering journal because there is a lot of intimidation from the move to real-time systems. Platforms such as the Edison or the Galileo provide engineers a smooth transition from simulation to invention. And for us as signal processing engineers, we try to solve a problem that, when taken out of a medical context, is familiar to any signal processing engineer. We were trying to estimate a transfer function. With a medical context, the engineering problem became an emotional goal, providing 100 million diabetics in third world countries an affordable way to control their blood glucose levels without any needles. With the Edison, this challenge was no longer just a computer simulation for us. We'll be talking about how an engineer perceives this kind of problems, about the move towards real time and from the lab towards reality. We'll talk about real problems that we are trying to solve, and we'll talk about a real solution for these problems. So an engineer looks at everything as a system. The human body for us is a system. A system has an input, a transfer function that changes this input somehow, and then output. This input could be sound waves, light waves, it could be radio waves, and the body will react in a certain way. And when sampling this wave as it comes out from the body, things change. As the body changes, so does the transfer function. And so if we map the transfer function and the change of the transfer function to body changes, we are able to estimate different parameters. We can, for instance, estimate the blood oxygen levels. We can estimate the glucose levels. We can maybe even estimate if there is a disease, if there is cancer. It's all in the waves as we channel them through the body. And it all depends on how accurate we are able to map the body changes to the transfer function. Some waves won't show us the information we need, but some waves might as well do. A little bit about machine learning. Machine learning for engineers allows us to outsource a lot of the difficult scientific questions to the machine, to the computer. I am not a chemist, and my friends aren't biologists or physicians, and we do not really know how different light waves interact with different molecules. But as engineers, we can input all of the data into some algorithm that receives lots of data, that we have no idea about the connections between different data points and different things. And we can look and we can give the algorithm some time and some ground truths and let it find out the connections. And so after the computer looks at the data during the learning stage, it can create a model that can then be used in order to classify things that weren't a part of the learning stage. For example, here we can see a different kind of learning. Sometimes we do not even have a ground truth. For instance, for a glucose meter, if we would like to learn about the way the body changes as in relations to the different wave outcomes, we can look at, as you can see here, the unsupervised learning, and let the machine find out different clusters and say, for instance, that this cluster means low glucose levels, and another cluster means high glucose levels. We can we can use supervised learning if we have lots of ground truth and we measured people's blood glucose levels prior to the experiment and checked the wave outcome. We can tell the computer what different data means and let the computer make the connection. After the computer makes the connection, we can then give the model to people that weren't tested, and we didn't have data about their glucose levels. And the computer will be able to use the model and the wave input in order to understand what is their blood glucose levels without any testing with needles. Semi-supervised learning is even a better technique, because sometimes you don't have a lot of ground truth and you don't want to invest a lot of money in testing using needles or stuff like that, and you can give the computer just a little bit of ground truth and let it understand for itself the different clusters. So the move towards real-time is a very difficult one for engineers. In the lab, you have all of your lab settings, and you don't have to start dealing with performance, with power consumption. You don't have to deal with different statistical outliers. You just use your MATLAB or another program that you can use in the lab and check the result. But in real life, people want to get the result very quickly. They want products that do not waste a lot of electricity or do not waste the battery too much. And we have to deal with a lot of statistical outliers. For instance, people are very different from one another. And some people may fit the model perfectly, but some may be very different. and a product such as ours cannot afford to fail because someone is just a little different, because after all, we are all just a little different. So what we were trying to solve, diabetes is not some rare disease that is unknown to the world. Lots of people around the world, according to the International Diabetes Federation, more than 300 million people have diabetes. It's not a disease that exists only in the Western world. Diabetes affects people all over the world, but the problem is that while in Western countries, stuff like diabetes meter and testing strips are subsidized, in the developing world, glucose meters and testing strips aren't subsidized, and so dozens of millions of people cannot afford them. When a diabetic is monitoring his or her blood glucose level, he's using one-time testing strips. These strips are very cheap, but can amount to lots of dollars each month, because they are one time and you are doing lots of tests. And so this is the problem we were trying to solve: how to reduce this price of monitoring. And so we would like to allow millions of people to afford the glucose meter and be able to monitor their blood glucose levels. Our solution does not involve any needles. Using the machine learning and transfer function estimations that I mentioned earlier, we are able to use infrared light and estimate the transfer function. And after creating a model during production, we are able to now estimate the blood glucose levels of a person that wasn't ever tested during the model construction. There is no needles involved, no testing strips, and so things are much more cheaper. We have a trade-off accuracy toward price, and our goal was to give a solution to people that currently have none. And so anything, and we checked with medical personnel, what is the threshold for us to be helpful towards people, so that we can make as much as a cheap device as much as we can, that will be accurate enough for these people to have a better solution than none. We have created something that is just a plug and play. The users can receive the glucose meter, our glucose meter that does not involve any needles. They can input their finger and get the result. And since we knew that people in developing countries may not have access to batteries or electrical sources, we decided to make it solar powered or mechanically powered, so that they wouldn't have to change batteries often or use outside electrical sources. And the whole thing does use a battery, but it recharges every time there is a light in the room. So glucose monitoring is just one problem, and many more can be solved using the same techniques that I was talking about. Estimating a transfer function and machine learning. You don't have to really understand the chemistry, you just have to understand the have a general notion of how different waves interact with the body. Intel's Edison can help solve many problems because it has lots of GPIOs, because it has low power consumption and very good performance. And we are hoping that other groups would use the same technology and help save lives and help find solutions to other problems. This is the end of my presentation, so I'll be happy to answer any questions you might have. I see here there is a question. There is an emphasis on helping others. Does this mean the schematics and source code will be made available open source? Currently, we are trying to understand how we can make it available to as many people as we can. We were even thinking about making the 3D model available to people so they could purchase little electronic kits, and they may even print at another location the product and just insert the electronic parts. We are discussing these possibilities with different people. Of course, there are reliability issues and stuff like that. We don't want people to use the code and then tell us it doesn't work because your code didn't work. Now I got errors in my glucose monitoring and may even affect lives. And so we have to consider how the implications of giving the code to people. But we are trying to find out how we can really give as many people the access to this product and in the cheapest way. Let's see if there are more questions I can answer. Does it need any setup or standardization before use? So our goal is to make it, as I said before, just plug and play. We are working on the model, so you don't have to make any calibrations or stuff like that. Just input the finger and watch the glucose levels. We are currently at a very early stage. We just had a competition a few months ago. But our goal is to make it, as I said, just plug and play. No need for any standardization or setup. Let me check for more questions. How much data did you crunch to get the transfer function? Well, we use an array of sensors in order to get as much accurate results as we can. We are sampling the data for a period of time. Of course, there is the price issue. We are trying to sample as much data as we can, but on the other hand, the more sensors we have, the higher the price that the users have to pay. We are trying to trade off these two issues, so we could give the users as cheap product as we can, but on the same time have better result, have an accurate result for them, so they could really monitor their blood glucose levels in an effective way. What programming language did you use? We are an electrical engineer. We are electrical engineers, and so when we started this project, we were using MATLAB, since for us it's the easiest way to program and use and test different algorithms for signal processing. For the Edison, we have wrote in C, so we could program the Edison, but that's about it. Let's see. What wavelengths do you use? Well, we use both visible and infrared light. We are talking infrared is can be divided into near infrared, mid infrared, and higher. The higher the frequency, the higher the wavelength, the more the price goes up. And so again, with the trade-offs, for us, we've tested different wavelengths, and we went as high as we can. But now begins the process to reduce the number of wavelengths and the frequency, so the product itself would be cheaper. Just a second. How do I type 1 diabetic can try your device? Well, we are currently. Oh, I see Jonathan answered this question, but I will answer it again. We are at a very early stage. We are currently working on the product. As soon as we can, we will start providing it to the world, and then you could start testing with alpha or beta versions, and I hope we'll get to a point where we can say that the device is now complete and can be used for people. And let's see. Just a second. About the core idea, so you use an infrared beam that is being transferred through the finger tip, and the output beam is being sampled, right? Yeah, exactly that. We are trying to see maybe the finger isn't the best organ to be tested. There are other points in the body that we can test. But for now, we are using the finger. When we get quite good results, we are trying to see if we can maybe other body parts can give better results. But again, different trade-offs come to mind, like price and the user interface and the ease in which users can use the device. Have you had approval from any medical authorities for where the accuracy is reliable enough to be used for in hospitals? Well, we have talked to many doctors, and we are currently talking to them. As I said before, we are trying to make it as cheap as possible, and as it becomes cheaper, the accuracy goes down. But we are talking to medical personnel in order to understand how low can we go, so we could make it as cheap as possible. Again, let's look at more questions. Do you measure the glucose levels in blood or interstitial fluid? Well, as I said before, we are not a medical. We have no medical training. We are not chemists or biologists. We see it as a transfer function. We test our results based on blood glucose monitor that does use needles, and we check how our results stand up to the results from the devices that do use needles. As I said, you can get an accuracy that is quite good in relation to these devices, but the problem again is to make it as cheap as possible. I have no, in reference to your questions, I have no idea exactly what I'm testing. I just look at it as a transfer function. Maybe I'm testing the blood, maybe something else, but I'm comparing my results to a blood glucose monitor.
Hey, Omri, maybe one last question, if there are still questions.
Okay. Have you thought about, on using the data to assess the amount of insulin required between shots? Well, I think it's too early to say. It might come in a much more advanced stage. Again, we are not physicians, and I don't have the amount of knowledge required to answer this question right now. But I guess as the project moves along, we would talk more and more with physicians and maybe try to improve the device as much as we can. For now, our only aim is to measure the blood glucose levels. Okay.
Hey, thanks very much, Omri, for this presentation and all those questions and answers. We're a little bit behind the half hour that was set, so I just wanted to wrap this up by leaving you with two additional links that are again more on the product side. And then obviously we'll send you an email where you can find replays of this whole presentation with the content from this team as well. So the first thing I wanted to leave with you is maker.intel.com, and this is really where you will find most of the product-related information and how to get started with these products. The second one I wanted to leave with you is software.intel.com/IoT. And this is where you will find more of the community help, software libraries and development kits to help you develop and find examples of code and samples of things that have already been developed with something like Edison. So with that, thank you for attending. I do believe that Beatrice had a last poll that you wanted to run, Beatrice?
Yes, absolutely. It's just to wrap up. There's a last question that we wanted to ask you, well, about what you thought about this webinar. I'll just leave you 30 seconds to answer that. Okay, perfect. So I will just close the poll now. I can see some last questions on the chat. Do you want to answer the last ones, Omri, or should we answer them via email?
And we tried to answer some of them now, but I think it would be better just to answer them via email, because I see a lot of questions and little time.
Yes. Well, we'll record this question. Perfect. And we'll answer them directly by email. Okay, so thanks everyone.
I think it's Thank you very much.
Thank you, Beatrice. Thank you, Omri, and the team over there, and thanks everyone for attending.
Thank you very much.
Have a good end of day. Bye, everyone.
Bye. Thank you.
Bye.